Okay, so let's talk about another example that is sort of similar to this very simple word count example, but has a slight change. Okay, so now we want to maybe know the makeup of a corpus of documents, a set of documents, and try to understand the characteristics of the word length. And so now instead of a histogram on word usage, we're going to group things by the length of the word. Okay, so we want to know how many words have greater than 10 characters and so on. All right. So, here we might group words into big words, medium, small words, and tiny words, where the big words are everything that's 10 plus letters, and the medium words are in red here, and they're everything from 5 to 9 letters, and so on. And you could define your own sort of bucketing scheme, or just not even try to bucket them and use the exact number. Okay. So, what we're basically showing here. So I'm hoping that some of you are already kind of seeing how this is a essentially trivial variant of what we already just did. And this is one of the points I want to make is that you'll see these patterns in designing MapReduce algorithms come up again and again. And so once you start to get a feel for how to do it, it won't be that every new problem looks different. But the other thing that's nice about maybe the next few slides, I think, is that it shows a little bit more detail in how these things are broken up. So for example, if this is a document, here, I guess the point I want to make is that before we sort of assume that every document was a small thing, but it's not impossible that you might have one document that's very, very, very large. This typically wouldn't happen with a document for various reasons, but imagine these weren't just documents, but these were just big data sets of words. And so every document itself, an individual document may be so large that it can't be processed by a single map function at a time. And so the question is, are we stuck here? Is the MapReduce framework broken and it's going to crash? And the answer is no. What will happen is when you load this large document into the system supporting MapReduce, and we'll talk a little bit more about what this lower level system is, what I mean by loading, the file system underneath MapReduce, underneath implementations of MapReduce. When you do that loading, the data set, the file, will automatically be split into chunks. And so we can pretend that this document was so large that it needed to be split into chunks. Okay. And so chunk 1 is this top part, and chunk 2 is this small part. Now, if a small document is underneath the chunk size, then it won't get split, but a large document will. Okay. And so this could have happened with the word count example too. This is not something specific to word length, obviously, but it's another twist that we're exploring. Okay. So fine. So now this top chunk gets assigned to map task 1, and it produces this little histogram of the counts of yellow words, red words, blue words, and pink words. And we can imagine, you should think about how the code might look if you had to write this, right? You would need to take the length, iterate over all the words in the document just like we did before. But now instead of emitting a key being the word itself, you would count its length and put in a case statement and figure out what color it is in this notation, and add that to a count. Okay, fine. So the output is these 4 key value pairs. And in chunk 2, we do the same thing and produce a different set of 4 key value pairs. Then in the shuffle step, all the yellow key value pairs will be grouped together, and there's 2 of them, and all the red ones will be grouped together, and so on. And then in the reduce phase, you'll add these 2 numbers together to produce 37. Okay. So the structure here is really identical to word count. It's just basically a change to the map function. And in fact, in this case, you could actually literally use the exact same reduce function. Right? For every key, add up all the contributions of it. You wouldn't need to change reduce at all. And this is something else you'll see, is that certain reduce certain functions are more general than others, and you'll reuse them time and again. For example, counting things and adding things up is pretty common in these MapReduce algorithms, and so general reduce functions that add things and count things come up time and again. Okay, fine. So word count, generally the canonical place to start when thinking about MapReduce. Word length, very minor variation on that. So let's think of another sort of minor variation on that, and this one arguably is even simpler than word count. So here we want to build an inverted index, and what an inverted index is when you have a corpus of documents, you can presumably efficiently access any given document by its name, right? So if you want to look up a URL on the web, you can do so. But for a search engine, a very primitive search engine, you might want to look up documents that contain a particular word. And so building this index to support word lookup to provide a list of document IDs that contain that word is called an inverted index, and it's one of the primitive steps in doing any kind of text retrieval kind of system. Okay, so now imagine we just had tweets instead of documents, and the input here is that the keys are these tweet IDs that I've invented, and the value is the text of the tweet itself. And so the desired output here is the word along with a collection of tweet IDs. Okay. So how do we do this? Well, again, the code is actually simpler than it was before, because now on the reduce phase, instead of, well, so we'll think about it for a moment. The map phase, instead of producing each word pancake in 1 for an occurrence, we won't do that. Instead, we'll put out pancake and the document ID itself, right? And all of these guys will be produced. And so this tweet 1, the map task that processes this tweet 1 will put out pancake tweet 1, love tweet 1, and so on. Okay. Further, an optimization here is if you see the word, I guess I should have had an example of this in here, but if you see the word pancake twice in the same tweet, do you need to put it out? Do you need to omit the key value pair twice? Probably not to build this index, because all you're trying to record is that the tweet contains the word pancake, not that not how many times it appears. So fine. So these key value pairs get shuffled across the network, and now the reduce task. What does it do? Well, it's going to get a key, pancakes. This should have an S on it, I guess. And it's going to have an iterator over all the document IDs that contain pancakes, which in this case is tweet 1 and tweet 2. So do we need to do any processing on this key and group of values? The answer in this case is no. The reduce function is non-existent. There's nothing to do, right? When the group is exactly what you want in this case. And this pattern actually shows up somewhat often as well, where you do want the map and you do want the shuffle phase to do the grouping, but all you wanted to do is to perform the grouping. You didn't actually care about the reduce function. So you're not counting these things, you're not adding them up in any way, you're not doing any processing on the tweets, you just want to omit that. And that's perfectly fine, because this group of values is perfectly serviceable as a value itself. Okay. So if you are used to, say, relational databases, nested structures, collections of values within a single cell in a table, in a single row, are generally disallowed, right? And this is actually first normal form, if you're familiar with that. But here we don't care. It's any key and any value. A key can have substructure and a value can have substructure. Okay, fine. So that's how to build an inverted index in MapReduce. Let me stop there, and next time we'll talk about this relational join example. So this will be how to implement a join from a relational database as a MapReduce program.